We'll be solving January 2026 Physics Unit 1 today. And in part 1, I'll be only discussing the MCQs. So the first MCQ says that which of the following is a scalar quantity? Now we have 4 options. First option says force, but what's the formula of force? Force equals to mass times acceleration, which means we are multiplying a scalar quantity with a vector quantity. Whenever we multiply a scalar with a vector, the answer is always a vector. And also we know by definition force is push or pull, right? So it has a particular direction. Either you're pushing something to the right, to the left, or whatever. It has a direction connected to it. So it is not a scalar quantity, it's a vector quantity. Next comes momentum. The formula for momentum is mass times velocity. Momentum is capital M. Mass times velocity. Again, we are multiplying a scalar quantity with a vector quantity. The result will always be a vector quantity, right? Which means momentum is also a vector quantity. Next, we have velocity. What is the definition for velocity? Velocity is speed in a given direction, which means it is also a vector quantity. And velocity is related to displacement. Next, we have work. Work done in formula is force times displacement. And usually it has an angle. So it's cos theta, which means that we have a dot product of vector, right? Vector times vector. It's not vector multiplied by vector. We have a dot product of vector because it is what? Force multiplied by displacement, which we can write as Fs cos theta, which is the dot product, which means the answer, whenever we have a dot product of vector, the answer or the result is always a scalar quantity. So work, it has a scalar quantity. Work is a scalar quantity. So our answer should be D. I have written everything that I've said. I have written it separately, so you can just pause the video and then look into it to understand it better, okay? Next, we have, all right, a vector diagram. Two forces, X and Y, act at a point. Which of the following vector diagrams shows the magnitude and direction of the resultant of the two forces? So whenever we have this head to tail vector diagram, there is always a rule that we have to follow. You start with your first vector. So we draw our first X vector. Now notice that all of these X, the first vector has the same direction to the right. So we don't have a problem with this, right? The second vector, Y, has to always start from the head of the first vector. The tail of the second vector has to connect to the head of the first vector. So it should be looking something like this, right? Now notice that in option A, we have the tail of first vector connected to the tail of the second vector. So this will not be the option, right? Let's complete this diagram. Now, according to the rules, the resultant vector has to be always connected from the tail. So the tail of the resultant vector has to be connected to the tail of the first vector and connected to the head of the second vector. So it should be looking something like this. This is our resultant. So the tail and tail has to match with the first vector and the head and head has to match with the second vector. Now let's see which of the diagram matches our diagram. This option B. In option B, Y, for the second vector, the tail of the second vector is matching with the tail of the first vector, which cannot be our answer. For number C, the tail of the second vector is matching with the head of the first vector. This is the head, right? So yeah, this is fine so far. The tail of the resultant force is connected to the tail of the first vector. So this should be our option according to the rules. I have written the rules for you separately. Moving to the third question. A copper rod was placed under tensile stress and tensile strain in the rod was measured. The graph shows tensile stress against tensile strain. Which does point X represent? Okay, so let's analyze. First option is given the fracture point of the rod. Fracture point basically means the breaking point, right? So where would it break? At the at the extreme end, right? This is the extreme point. After this, there is no graph, which means that after this, my rod is broken. So this has to be my fracture point, right? This is my fracture or breaking point. After this, there is no graph, right? Then it says the limit of proportionality. Okay, the limit of proportionality ends where the proportionality ends. This is a straight line, and I think the proportionality ends almost here. So this should be my limit of proportionality, which is way before x. So x cannot be limit of proportionality. Number C says the maximum tensile strength of the rod. The maximum tensile strength is after x, not at x, right? This is the maximum point. Number D says the yield point of the copper. Yeah, this could be the answer because after limit of proportionality, for some time, at this particular point that I've marked, for this particular point, if the force on the rod is removed, the rod will return to its original position, even though there is no limit of proportionality. So the force will not be directly proportional to extension. But at this point and after this point, the material, the rod, will start to deform plastically, which means that it will deform permanently. After this point, even if you remove the force, it will never ever return to its original shape ever again, right? So this should be the yield point, after which even you can see after this point X, the material does not hold its shape, right? It has deformed permanently. And after this, it just breaks, right? So this should be my yield point. Moving on to number 4. A tractor pulls a trailer a distance s in time t. The useful power output of the tractor is P. Which of the following equations gives the force F of the tractor on the trailer? So we are given power, which is P. We are given distance s, and we are given time. And we are supposed to find force. Since it is related to power, let's write the formula of power. Power is equals to work done by time taken, right? And work done is related to force. So we can write work done equals to force times displacement divided by time, which is equal to power. Now we need to isolate force. So power equals to force S. So what will be force? Force will be PT by S. So my answer should be B. Number 5, a cylinder of aluminium has a weight of 35 newtons and a volume of 1.3 into 10 to the power minus 3 cubic meters. Which of the following calculations gives the density of aluminium in kg per meter cube? All right, so the formula for density is mass by volume, but we are given weight. So we are just supposed to convert the weight to mass. Weight equals to mass times gravity, right? So mass is equals to weight divided by gravity. 35 divided by 9.81. So we just place it here, 35 divided by 9.81, and we have our volume. And what is the value for volume? 1.32 times 10 to the power minus 3. Let's see, what does it match? It matches C. Easy. Number 6. An object on the moon falls a vertical distance of 0.3. Okay, so we are given displacement, which distance, which is 0.32 meters from rest. So u equals to 0 in a time of 0.63 seconds. Which of the following expressions gives acceleration due to gravity? So this matches our SUVAT, right? According to the SUVAT, if we are given distance, initial velocity, and time, and we are supposed to find acceleration, we can use this formula. S equals to ut half at squared. Now S is given to be 0.32. Ut, since u is 0, ut becomes 0. Half a into t is 0.63 squared. Now if we isolate a, it becomes 2 times 0.32 divided by 0.63 squared, which is a. What does it match? It matches this particular thing, C. Answer should be C. Easy, once again. Now, number 7, A sphere falls through a viscous liquid as shown. Which row of the table describes the upthrust and viscous drag on the sphere as it accelerates downwards? All right. Um, let's see what happens to upthrust and viscous drag in this particular image, right? See that the sphere is completely submerged in the liquid, which means that upthrust, what is upthrust? Upthrust is the volume of liquid displaced by the object, right? And since the sphere is completely submerged, it has already displaced all of its volume, or it has already displaced a certain amount of fluid to the surrounding, which is equal to its volume, right? And its volume is not increasing or decreasing because obviously it's the same sphere. So as the volume of the sphere is not changing, the volume of displaced fluid is not changing. So upthrust is also not changing. Upthrust will remain constant, which is what I have already written here. You can pause and read it out. Now which means that upthrust will remain constant. So our answer has to be something between B and D. Let's see. Now coming to viscous drag. For viscous drag, we basically have a formula, right? Fd is equals to 6 pi r eta v. Among this, 6 and pi are constants. So viscous drag depends on radius, it depends on eta, which is viscosity, and it depends on velocity. So if speed increases, if the speed of the ball increases, then viscous drag will also increase. If the radius or surface area increases, then viscous drag will increase. If viscosity increases, then viscous drag will increase, right? Because they are proportional to viscous drag. Now, they said it accelerates downwards, which means the speed of the sphere is increasing downwards. Speed increases downwards since it's accelerating downwards. What did I say? If speed increases, then viscous drag also increases because they are proportional to each other. So our answer should be number B. Upthrust is constant and viscous drag is increasing. I have written this thing as well. You can pause and read. For question 8, we are asked two arrangements P and Q of identical springs are subjected to the same tensile force. Which row gives the total elastic strain? So what do we know about elastic strain? Elastic strain is half Fx, right? Now, since nothing is mentioned about the extension, we can eliminate this extension from the equation. How? Because we know F equals to Kx, right? So x is equals to F by K. So let's replace this x with F by K. Half F, this F is this one, and then half F into F by K. Just replaced the x, so it becomes E is equals to F square by 2K, right? Now let's see. For springs connected in series, K is equals to half K, right? And for parallel, K is equals to 2K. We know these by some derivations, right? So now let's replace the K in this equation by these to make two particular equations for series and parallel. Now for this one, E is equals to, let's say ES, okay, 2K. If I replace this K, it is half K. Now if I take this half out, can I write E is equals to, this half will go to the top, so it will become 2F square by 2K, right? Now I'm not crossing them out because if I just place this here, if I place this 2 outside the fraction, it looks something like this, right? F square by 2K. Now we have F square by 2K that can be replaced by E, because we know F square by 2K is equals to E. So ES can be written as 2E. And for parallel, same thing, EP is equals to F square by 2K, and this K can be replaced by 2 here, 2K. Now I can write it as, this 2 can be written as half, right? because this is in the denominator and at the numerator I have a 1. So it becomes half, and I can write f square by 2k. Now again we can replace this f square by 2k by e. So EP is equals to half e. Now so for series we have 2e, and for parallel we have half e. D matches our equations, right? So the answer should be D. Force. When the force is gradually decreased, the rubber band returns to its original length. Okay, so a certain amount of force is given on the rubber band, which is why this is the loading graph. And then if you are removing the force, this is your unloading graph, right? And the extension is 0, as they have mentioned. PQR represents areas of the graph. Which of the following gives the work done in stretching the rubber band to its maximum extension? They have said work done in stretching the rubber band, which means they mean about the loading one, right? Where you are exerting the force and the rubber band is stretching. So we are talking about the loading graph. Now, what do we know? Work done is equals to force times distance. In this case, the distance is extension. So work done is equals to force times extension, right? See that we are multiplying the y-axis and the x-axis, which means the area under the graph is equal to work done, right? Whenever you multiply the y-axis and the x-axis, the area under the graph is your answer. So we are basically talking about the area under the graph, which is Q. This is the area under the loading graph, under the loading graph, Q and R. So it should be Q plus R, which is option B. Last question, number 10. A person is pushing a trolley at a constant velocity. The floor exerts a force W on the person. Okay, so floor exerts a force W on the person. The person exerts a force X on the trolley. The trolley exerts a force Y on the person. And the total drag force on the trolley, the drag force should be this one, is Z. Now, according to Newton's third law pair, you're supposed to find which pair of forces is Newton's third law. According to Newton's third law pair rule, the forces that you're exerting have to be the same type. They have to have the same magnitude, and they have to have opposite directions. They have to be acting on different bodies. Notice that X is acting from the person to the trolley. Y is acting from the trolley to the person. So we are talking about two objects here, person and trolley. They're opposite in direction, right? So this should be our answer, X and Y. B. Why not W? Because W is being exerted from the floor to the person, but the person is not exerting any force on the floor, which means that it does not have a pair. Then again, trolley is exerting a force. A force is being exerted on the trolley because of the drag force, but the trolley is not exerting any force, right? So that should also not be working as a pair. So our answer should only be X and Y. So we are at the end of part 1.